So now that Ross has provided a relatively detailed overview of our protocol augmentations, it's important to discuss the high-level network constants that we set so that we could run our experiments on top of. As stated previously, at the core of our assumptions, we are assuming that these nodes are static, as in their position is constant. In NS3, this is implemented through a class known as the constant position mobility model, and it is pretty aptly named. It is a model that allows you to specify a position as a 3D vector, as in specify the x, y, and z coordinates, and then those positions will be set until they get changed, in future experiments. In addition to this, we created an ad hoc Wi-Fi network, which is a decentralized design pattern that allows communication without various infrastructure components like routers or access points. Since communication in our experiments is supposed to replicate the exposed node problem, no traffic is intended on leaving our local network, and as such, we don't need things like routers and access points to further complicate our network topologies. In addition to ad hoc networks with static nodes, we had to define certain propagation delay models and propagation loss models so that we understood when packets were being lost, how far away our nodes had to be, and who could end up communicating with who. Without getting into too many details, there were various classes within NS3 that we modified, and ultimately we ended on kind of the fundamental physics assumptions in Wi-Fi networks. So this includes the distance squared propagation loss, where signal strength attenuates proportional to the square of the distance between two nodes, as well as a propagation delay following the speed of light in a vacuum. On top of these physical constraints, we tried as best as we could to adhere to the 802.11g standards. The 802.11 family of standards generally encompasses popular wireless local area network construction. Specifically, we chose the 802.11g variant because of its popularity around the world as well as its relative simplicity. Overall, this standard has a minimum supported data rate of 6 megabits per second, and we decided to stick to this rate for maximum transmission in order to fully saturate links when convenient without overly taxing our computing resources. Additionally, while specific numbers might vary depending on the standard that we use, we are assuming that the overall trends of our results are going to maintain constant. So whether this was 6 megabits per second or 54 megabits per second, which I believe is the maximum supported, we believe that the overall patterns of our results would maintain constant. So now that we have all of our parameters set, we decided to replicate the exposed node scenario. This little text representation of our topology is analogous to the graphic that we showed before. It is the standard exposed node setup, and those numbers underneath the various nodes represent their positions. In its most basic form, we are assuming that these nodes are in a linear fashion, so they only have x coordinates, and based off of our physical constraints defined previously, these constants ended up being 0, 200, 800, and 1,000. So what this means is that node 1 and node 2 can hear each other. They are 600 distance units apart, and node 0 is out of range of node 2, and node 3 is out of range of node 1. All of these values were determined based off our physical constraints, and we calculated these through a combination of trial and error and calculation. We knew the propagation delay and our propagation loss, and we knew that we could set our physical locations. So this was simply have two nodes sending, move one node further and further away until they can no longer communicate with one another, and then place them accordingly. So as far as generating traffic, we had nodes 1 and 2 generating 2048 byte UDP packets at an interval of 0.003 seconds and for a duration of 5 seconds. So this was intended to essentially saturate the link for node 1 and node 2, as in node 1 and node 2 both want to use the maximum link bandwidth for the entire duration of our experiment. And nodes 0 and 3 aren't generating any traffic. They're simply servers accepting all the traffic from node 1 and node 2. So as far as our preliminary results, this is about what you would expect for the exposed node problem. Since node 1 and node 2 both want the entire link bandwidth the entire time, and only one of them can have it, they ended up splitting this bandwidth, about 50-50. You can see this TX offered represents the total throughput offered for transmission, which ended up being about 5.5 megabits per second. And the throughput that they actually gained, as in what the receivers ended up receiving and what they ended up actually sending, was 3.6 megabits per second. And the transmission offered versus lost packets, we actually didn't end up losing any packets for this. TX offered just means we queued up these packets to be sent, and then nothing was ever sent by the time the experiment ended. So while these packets weren't lost, we didn't end up getting that much throughput. And walking through this graph a little bit, the green line represents the node 1 sending rate, the red line represents node 2 sending rate, and the axes are packets per 100 milliseconds versus time. So this is essentially another representation of the throughput for each of our senders. And that was an overlay of the two. This just demonstrates what our receivers actually received. And if you alternate back and forth, you can see that they received everything that the sender sent, as in no packets ended up being lost. So now once we turned on our protocol modifications, you can see that the TX offered and throughput achieved was, 100%. This indicates that nodes 1 and node 2 were able to actually take the channel and send their information across, and their recipients were able to receive all of this information unobstructed. We weren't able to do an overlay graph in the exact same way due to limitations within Wireshark, but you can see that the packets per 100 milliseconds for both of these senders is right at around the maximum of what they desired. And while there are slight deviations in this over time, there is some probability associated with these results, and part of our remaining work is interpreting exactly what is going on during these different scenarios.
And so this brings us to our remaining work. From here, we have accomplished a lot. We essentially took a crash course in C++. We learned the ins and outs of NS3, both at the user level, creating networks and network topologies and making sure to set all the parameters exactly to what we wanted them to be, as well as down into the source code level, understanding fundamentals of IEEE 802.11 standards and fundamentals of networking in general, in particular wireless networking. All of this allowed us to, we believe, accurately construct our modification and to accurately run simulations on it. Now, moving forward, we hope to extend the breadth of these topologies and to kind of vary all of our free parameters to see exactly how our modifications perform with various network densities, various network topologies, and various assumptions about distances between nodes and various traffic patterns as well. All of this expansion will allow us to kind of see the big picture of how this algorithm performs versus the original algorithm. Although our preliminary results have been positive, we kind of want to see the full extent of in which directions this algorithm outperforms and under what scenarios this algorithm just can't keep up. Thank you.